Okay, today's problem is another problem out of Morin's Introductory Classical Mechanics textbook. And the question is basically this. Imagine you are some distance L away from a vertical wall, and you want to throw a projectile, and you want to throw it in such a way that it hits the wall as high as possible. So you want to hit the wall at the highest possible point on the wall. Now we can't control how fast we throw it, so V naught is just going to be the launch speed. That's a fixed value, but we can control the angle. So the question is basically what angle should we launch this at to maximize that height. Okay, so let's go ahead and just call that height y. After all, it's the location on the trajectory that the projectile will have at position x equals L. And we can just jump straight into the trajectory equation. Okay, we've seen this a couple times before. What we now want to do is plug in x equals L, because that'll be the location of the wall. And then we'll want to maximize this y with respect to theta. So take a derivative and set to 0. Okay, so remember that the derivative of secant squared is going to be 2 times secant theta, that's from the chain rule, and then times the derivative of secant, which is secant tangent. And we want all of this to equal 0. Well, for starters, we can go ahead and get rid of one of these L's. We can also see that there is a secant squared theta in both terms. And since we're not looking at any place where secant equals 0, in fact, secant never equals 0, we can divide those out. So secant squared, secant squared. We can also get rid of this 2. And we end up with the pretty trivial result, or at least not too complicated result, that tan theta, moving this over and doing some cross multiplication, is V naught squared over GL. Notice V naught squared over GL is dimensionless, which it has to be a tangent of an angle. And so theta, the theta that maximizes this height, will be the arctangent of this quantity. Now, while we're at it, let's check a couple other things. I mean, that's the answer to the question. But first off, now notice that this quantity, V naught squared over GL, does have a constraint. And the constraint comes from the fact that if I want to hit the wall at all, it can't be further away, the wall can't be further away than the maximum range. And you might recall that the maximum range of a projectile is V naught squared over G, and that's at theta equals 45 degrees. We've worked that out before. Since we require L to be less than R, that actually forces V naught squared over G, which is R, divided by L to be greater than 1. In other words, the tangent of this angle does need to be greater than 1, or else you just won't even hit the wall, let alone hit it as high as possible. So there is a constraint on the value of L that'll make this work at all. And because this is greater than 1, that actually tells us that theta itself has to be bigger than 45 degrees. Tangent is an increasing function, it's monotonic on the interval we're interested in. And so if tan theta is greater than 1, then the arctangent also has to be greater than the arctangent of 1, which is 45 degrees. So we do have to aim a little above that maximum range, giving theta to maximize the height here. The other thing we might want to know is, well, where in the trajectory does this actually hit? The way I've drawn it, it makes it look like we hit the wall after we've reached the maximum height. That actually is true, but let's see why that is. Well, notice that here, the halfway point is R over 2. So if I went and calculated R over 2 in terms of my given parameters here, okay, so we know how to calculate the range of a given projectile. So that gives us V naught squared. I would normally have a sine 2 theta. I'll expand that out as a 2 sine theta cosine, but then the 2 cancels. So I'll just have a sine theta, cosine theta, all over G. Okay, so that's the generic half range of any projectile. In our particular case, we want to substitute in this value of tan theta, and see where that lands us in terms of this L. Easier way is probably just to substitute V naught squared over G as L tan theta. So this will be L tan theta sine theta cos theta. Notice that that's definitely just L sine squared theta, which is also definitely less than L. So R over 2 is less than L. That's telling us that this halfway point actually is earlier than the location of the wall. So yeah, we do actually hit it on the way down when we're maximizing that particular height on the wall. Seems a little strange. It seems like, well, isn't there some way we could choose so that the wall is right on that maximal height? You can, but then it turns out you could do better by aiming it up a little more and hitting it after a different max height. So that's kind of interesting. Okay, last thing I want to do here is calculate what is that maximal height and compare it to this capital H, which is the max height of a general parabola. So let's erase this and get that going. Okay, so I've rewritten our trajectory equation in terms of the location of the wall, L, and also we're trying to find the maximum height, I'll call that Y star, in terms of this maximum height finding angle tan theta, which, by the way, we've found. V naught squared over GL. Okay, so plugging in this tan theta star will give us something in terms of only the parameters of the problem. To do that for secant squared, let's not forget the Pythagorean identity that secant squared is 1 plus tan squared. So we can find that Y star is going to be L times V naught squared over GL, that comes from the direct substitution, minus GL squared over 2V naught squared. And then we've got our Pythagorean identity, 1 plus tangent squared. That'll be V naught squared over GL squared inside of there. We can do a little more simplification here. The L's here cancel. Notice that when we expand that out, we'll get V naught squared over G. This first term can't do much about. V naught to the fourth over V naught squared leaves a V naught squared in the numerator. And then the L squareds here and here cancel. G over G squared gives me a G downstairs. Notice that I have a V naught over G minus a half V naught squared over G. And so we can simplify once more. And I'll go ahead and pull that whole thing out. So I'll have V naught squared over 2G. There's one of those left from simplifying these outer terms. And then on the inside, pulling out additional terms will give me, what do we have? The 2 already came out. So I'll have V naught to the fourth down here and a G squared L squared. And actually, let's go ahead and just write that in terms of our little GL over V naught squared squared. Okay, so this is one way of writing down Y star. And notice that V naught squared over 2G can be factored out kind of nicely as a common dimension. On the other hand, we also have the old formula for the maximum height that we've previously found. This has been calculated earlier, so really all we have to do is now plug in what is sine squared theta if tan theta is equal to this. Well, there's a couple different ways of doing that. Probably the easiest is to draw a little triangle. So thinking over here, this is not a real triangle, it's just sort of a fictitious triangle here. Here we have our theta. Thinking of tangent as opposite over adjacent, where it's V naught squared and GL, then Pythagoras will give us this last bit, V naught to the fourth plus GL quantity squared. And now we can just read off sine as opposite over hypotenuse. So if we want to go ahead and simplify out the H in that case, we'll have V naught squared over 2G. That's the same factor we pulled out here, so it'll make comparison easy. And then sine squared is going to be opposite, that's V naught squared, over hypotenuse, which is this radical. And then don't forget it's sine squared, so we should square all of that. And now let's kind of do the same thing we did here to write it in a form we can recognize. This is v naught squared over 2g. And then if I factor out a v naught squared from this root, well, I guess after canceling, so the root is gone and this becomes a 4, I can pull that v naught to the 4th out, and I'll write this as 1 plus gl over v naught squared to the minus 1, just to make it look the same as this one. And now we can kind of directly compare these and say, oh yeah, because I'm subtracting a thing in here, 1 minus something, whereas here I'm adding something, even if it's in the denominator, we do end up saying that y max is less than h. Okay, so what we've done here is we've found the magic angle that maximizes the height of hitting a wall that's a fixed distance away, and we've shown that it actually ends up being the launch angle is higher than 45 degrees, and that it hits the wall at a point after the apex of its trajectory, and we even found an expression for that maximum height, QED.